So in the past, we have seen that if there are multiple random variables, you can write one variable in terms of the other random variable. So we have seen the cases where there are two random variable x and y. So you can represent y in terms of x. So here we try to make this more formal. Let x be a random variable in the probability space omega fp. Then we can define a function on x. This takes value from the range of x to a real line. So you can see here, suppose x is a random variable, so it maps different outcomes to real line. So if this is one outcome, it is mapped to this value. If it is another outcome, it is mapped to this value. Then all these values which make the range of x, these are the values random variable x can take. Now, if I define a function from the range of x to real line, this function g will take one value in the range and map it to some value in the real line. So this particular g, there is one example of g I have considered that this and these two are mapped to this value and this is mapped to this value. And suppose there are three values in the range. So now these are the range of the g would be, now in this case would be these two values when they are applied on the range of x. So this is a composition of function. X maps from small omega to some values in real line, and then g takes these values and map to some values again in the real line. So I can combine these two function as a composition and can get a single function which maps omega to the corresponding value in the real line. So this value is mapped to this, and then g maps it to here. So this composition of function g of x will map this to this value. Similarly, this will be mapped to this value. This is also mapped to this value, and this outcome will be mapped to this value. So this can be represented by, if I just forget about x, this composition can be equivalently represented by this map. That these three values, these three outcomes are mapped to this value in the real line, and this outcome is mapped to this value in the real line. Okay, so what is this map? This map is mapping outcomes to values in the real line. So this is also a random variable y. Okay, and then you can prove that if this g is a valid function, then y will also satisfy other properties of random variable given x is a random variable. So if we denote this y as g of x, okay, so this is the notation, but actually it means that y is a random variable. Okay, y is not a value, it's again a random variable. So it's a function from omega to real line. So this means that for every outcome, when I say y equal to gx, I mean that for every outcome omega, y omega is equal to g of x omega. So you take omega, you compute x omega, and then you compute g of it, so you get y omega. So this is the new random variable. Okay, so suppose g equal to x square. This means you, for any omega, you take x omega, then take x square omega, and then that's how you get a y omega. Okay, and then if you know x and g also, you can write y directly in terms of omega. Suppose x omega is omega, then x square omega would be omega square. Then I can just say y omega is equal to omega square. So y omega can also be written as a direct function, or it can also be written in terms of x. Sometimes we do not know exact value of x. In that case, expression of y in terms of x can be helpful. If you do not know the exact value of x, how it is mapped from omega to real line, but if you know the distribution of x, then we can calculate the distribution of y also. In that case, it is not required that you need the complete information of X. But if X is known and G is also known, then you can either compute the distribution from distribution of X, or you can directly write Y in terms of omega and then can directly compute distribution. We will see these examples later on. But first, here we will talk about what is the expectation of a random variable. So we'll start with a very simple example. We take a discrete random variable X. Suppose it takes two values A and B. So an example can be a random variable which takes value 1 and 2 with some probabilities. Now I want to compute the mean value of X, the average value of X. So it may mean that if I do this experiment multiple times, if I average all the values, what value I will see. This also represents that if you are, suppose, betting in a game which where the earning is a random variable, then how much you can expect to win, that can be connected to the expectation of the random variable. So anything which gives a sense that what is the average value of this random quantity, that is expectation of that. So how can we formally calculate it? So let us take this example that X takes two values A and B, and suppose they take A happens with value PA and B occurs with value PB, and then of course PA plus PB should be 1 because these are the only two values. So you can take example, suppose this is 30.3 and this is 0.7, 30% and 70%. So suppose if you do this experiment multiple times, n times let's say, then you can expect, because this occurs with 30% chance and this occurs with 70% chance, you will see that out of n, 70% times you get an A. Sorry, this is 30, this is 70. So 30% time you get A, and then 70% of time you get B. Okay, so if this is PA and PB, this means that NPA times you get the outcome is A, and NPB times you get the outcome is B. So they are total n values, and NPA values are A, and NPB values are B. If someone asks you take all this data, take all the n values, and compute the average, okay, then it means when you sum it, so for average you have to sum it and divide by n. When you compute the summation, then you will count A NPA times because they are NPA samples with value A, and then you will count B and PB times. So total summation would be NPA into A plus NPB into B, and then you divide by n. This will be your average. We call it sample average because you have taken many samples and then you are then just computing the average. So what is this value? This n will cancel and what you get is APA plus BPB. What is this? This is a weighted average of A and B. Okay, so what is this way? Basically, you are trying to compute the average of A and B, but you multiply the probability of A and B as their weights and then compute the average. Okay, this makes more sense. Let us see this way, that suppose A occurs with almost one probability, almost 100% of time A comes and B rarely comes. Then what will be the average? Average should be equal to A because B rarely occurs. So in that case, what I do is I take the average of A and B, but I multiply 1 cross A and then 0 cross B to compute the average. So I'm giving 1 weight to A and 0 weight to B because B doesn't occur. Similarly, if both occurs with half and half probability, then I will take 1 half into A plus half into B. I'm giving half and half weightage to both. And then suppose B occurs with 100% probability and A doesn't occur, or A occurs with a very small probability, then the weightage will be 0 cross A plus 1 cross B. So average will be B. So depending on what probability they are occurring, the average can be A, B, or any value in between, like A plus B by 2. So this is that weightage. This probability of A occurring tells that when I do this experiment multiple times, the average is more likely to be something which occurs more times. Okay, so that is why when we compute the average, we multiply by the weight of the probability of that value occurring. So in that case, the average will be APA plus BPB. And this is denoted as the mean of this random variable, EX, which is equal to APA and BPP. So see, there are two ways to compute the mean. One is if I know the distribution, I will take the two values, multiply by the weight of their probabilities, and just add them. Okay, so this is not just a simple average A plus B by 2. It is an average which is weighted by the probability. Or another way is you can do this experiment multiple times and then add all the values and divide by total number. Here there is no weighing we are doing extra. We are just adding all the values. But because the values which occur more of the time, when you add them, they will be added more times. Okay. So suppose this occurs with 30 and 70%. Then when you add them, you will see A 30% times and B as a 70% times. So when you add all those values, you will of course see a average which is more towards the value B. So we are not doing any weighing in this explicitly, but there is an inherent weighing when we compute the sample average. Or we can directly compute, if I know the distribution, I can compute the average by just taking a weighted average. This can be further extended to random variable, discrete random variable, which takes more than two values. So let's consider a discrete random variable x, which takes range R with probability pxx. So suppose range R can be countable or finite. There are some numbers and then probability corresponding to those values as this. Then the average is defined as summation over all values in the range. You take the value x and then multiply by the weight of the value. So this is a weighted average. This is a weighted average of all the values x takes, and the weight are the probability with which the x takes those values. So if there are only two values, you just take two values. If there are three values, you take three values, multiply with the corresponding probabilities and add them. Okay, so this can also be written using the definition of PMF, that you add over all values which x takes, which are in the range of x. You take for all those values, you take the value, multiply by the probability that random variable takes that value. Okay, and remember, mean can be infinite as well. If random variable takes this summation, when you calculate, can become infinite also. Similarly, instead of just E of x, so this is expectation of x, I can also calculate the expectation of any function of x. Let's take E of x squared. Okay, so this means if I do this experiment and calculate x squared every time, what is the average of values I will see? So this again the same concept. You take x squared and you add all those values. Suppose you do the experiment n times, you get n values. Each value represents some x square. If you add them, if x takes two values a and b, npa times you will get a square and npb times you will get b square. So average will be the weighted average of a square and b square, and the weighing is by the probability. Okay, so this average would be nothing but the value of x square weighted by the probability that x occurs. Okay, so if there are two values 1 and 2 with probability 30 and 70%, then if 1 and 2, then mean x square will be 1 and 4. So this means x square is 1 with 30% of chance and 4 with 70% of chance. So expectation of x square would be 1 into 0.3 plus 4 into 0.7. Okay, so we are not doing anything on the probability because probability just denotes what is the chance of that one occurring. Okay, the value instead of x will be x squared. Similarly, if you give an arbitrary function g and ask you to compute the expectation of g of x, then this is same way. You take all the values x can take, compute gx corresponding to that, multiply by the weight of this x occurring, for which the gx will take the value gx, and then you add on. So this is for discrete random variable. If this is a take finite value, this will be finite sum. If this is a countable some values, they take countable, the range is countable, then there will be a countable infinite summation. Now, how do we extend this to the continuous random variable case? So in continuous random variable case, X does not take some countable or finite values. It can take all values in an uncountable range. So in that case, we don't have PMF, but we have a PDF. So suppose this is the PDF of X, the red one, and this takes value between A and B. Now I want to compute its expectation. Okay, so let's do a simple exercise. Let quantize the values X takes. So instead of saying that it takes all values in between A and B, I will say I will divide the whole interval into small intervals of width h. So A to A plus h, then A plus h to A plus 2h, A plus 2h to A plus 3h. So total number of intervals would be B minus A by h, and the ith interval would be from A plus ih to A plus I plus 1h. Okay, and I'll start with 0th interval. So if you think about this particular interval, then actually x can take any value in between. But let's assume that I am replacing the values of x by the middle value of this interval. So if any value, so if I do this experiment and x takes any value between this two range, then I will just replace the value by the middle value, xi plus xi plus 1 by 2. Okay, or this means if you fall in the ith interval, xi takes a value in the ith interval, then I will replace the value of x by a plus ih plus a plus I plus 1h by 2. Okay, see, this is a mean. I'm computing the mean. So if this range is small, then replacing it value by the mean may not change the total value by a huge margin. Right? Let's think that I have taken h, suppose 0.001, and xi is 3, then this will be 3.001. So if I replace any value between 3 and 3.001 by just 3.0005, this will only change the summation by a maximum of 0.001. Okay, that is not a very big change in the summation. Okay, of course it will not be accurate, but it will be close to the answer. So clear? So we have all these n intervals and we quantize the value. When random variable, we do the experiment and get a value, we first find which interval it belongs to. Suppose it belongs to this interval, then we replace its value by this. So this means if I get 3.008, I will replace it by, sorry, 3.0008, I will replace it by 3.001. Sorry. This is 3 and this is 3.01. So if I get a value 3.008, I will replace by 3.05, the middle value. So this complete, if I do the experiment multiple times, I get n values and I each quantize them by the middle values. Then instead of getting all those possible values, you will only see x taking the middle values. Okay, this will become a discrete random variable. Okay, and what is the probability that the x, we will see a value equal to the middle value of this bin? Okay, so all this will be equal to the probability that x takes a value in this interval. Okay, so if x takes any value, then I will replace it by the middle value. So probability that in the quantized version I will see this value is nothing but the probability that x actually lies in this interval. And what is the probability that x lies in this interval? Remember from the PDF definition, if I take a very small interval, the probability that the random variable takes a value in this interval is equal to the density multiplied by the length. So length is h and the density is fxi plus xi plus 1 by 2. Okay, and I'm assuming this is a very small interval, so density will be almost constant. Okay, so this h is very small. So the probability that xi belongs to this bin bi is equal to the PDF into h. Okay, I have taken here the PDF at the left hand corner. You can take left hand corner, right hand corner, the middle one is not going to change a lot, assuming the density, the interval is a small interval. Okay, so this is known as the Riemann approach. And what we are doing is, instead of taking all the values, I am approximating values. So I have divided into n intervals, and if for any bin, if xi falls to any bin, I replace the value, I quantize the value by the middle one. So say discrete distribution, the contrast distribution converts to a discrete distribution with all those n values it take, with n probability of each n value is also given by this. So how can I compute the expectation now of this discrete random variable? Recall if there's a discrete random variable, the mean is just given by summation over the complete range of the value multiplied by the probability of that value. Okay, so from this calculation, the mean would be given by summation over I from 1 to n xi, and then PDF into s. This is the probability. So your xi and the probability that it takes value xi is fxi by h. Okay, and these xi are these small intervals a plus ih. Now this is also always an approximated value, and it will be better if I take this h small and small. When h is very small, then this discrete random variable will look like a continuous random variable. So let's take the limit s tends to 0, and you know that if you have such summation over different small intervals, and if you take s tends to 0, this summation will become a integration. So here, when I take limit s tending to 0, this expectation will become integration over the complete range x, fx, and h become dx. Okay. So this range can be even infinite, that does not change anything. So if x takes all values from -20 to plus infinity, this integration will be -20 to plus infinity. If this is just from a to b, then limit will be from a to b. Okay, so here also just remember x is the value and fx dx is the probability that x takes value in this interval around x. Okay, so we have divided the whole range into small interval of size dx centered around the value x. So x takes that value with probability fx into dx. So if I sum it over all intervals, I get the total expectation. This is also true if I take any function of x. In same way as the discrete random variable, you can prove that E of gx is nothing but the integration over the range gx fx dx. Okay, this you can prove the same way. Instead of taking the value x, when you compute, you can quantize it. get the discrete random variable, then when you compute the expectation, instead of summing over x into probability of x, you will sum over gx into probability of x. And then when you take s tend into 0, this will turn to an integration of this form. We will end the discussion with one result which we use a lot. This is true for a positive random variable. So let's take x is a positive random variable. It means x only takes value in the positive domain. X cannot be negative. So in that case, I want to compute the integration of CCDF dx. CCDF is the complementary CDF, is the probability that x takes value more than small x. So let's compute this integration. So I'm integrating from 0 to infinity of the probability that random variable x is greater than small x dx. So px is nothing but 1 minus probability that x is less than or equal to x. Okay, probability that x is more than x is, this is probability of a is equal to 1 minus probability of a complement. And this is a, then a complement would be x is less than or equal to x. So this is nothing but 1 minus probability that random variable capital X is less than or equal to small x, and that is nothing but the CDF. So this is equal to 1 minus CDF of x into dx. Okay, and what is CDF of x? This is nothing but the integration. The whole thing is nothing but the integration of PDF from x to infinity. Okay, recall, this is the probability that capital X takes value from between x to infinity. So probability of that will be just integration of density over x to infinity. Okay. And then there is an integration outside of dx. Okay. Now I do a trick. I will switch the integration order. Okay. So you may have learned that if there is a two-dimensional integration, you can switch the limits. So this dt will go out and dx will go inside. This limit will also switch. So outside limit was x and t goes from x to infinity. When the limit switch, then t would go from 0 to infinity and x will go from 0 to t. Okay. So t is going from x to infinity. So t was more than x. Okay. So this means x will be less than t. So x will go from 0 to t. So if I integrate this first, this will be just x from 0 to t, which will give me t. And then there is a after dt. So the integration of t after dt is nothing but e of x. Okay. So this is actually fx, just denoted by f. So this means that if I take a random variable, positive random variable, and compute the integration of CCDF, I will get the expectation. So this is another way to compute the expectation of a random variable. Instead of integrating this whole thing, if I know the CDF, I can compute the CCDF and compute the integration. Just as we computed the expectation of one random variable, we can also compute the expectation of a function of many random variables. We will start with a very simple example. Let's take two random variables, x and y, and suppose they are independent to each other. So we know that if two random variables are independent to each other, this means, and I am assuming them to be continuous random variables. You can prove the same thing using discrete random variables also. So if they are continuous random variables, they will have a PDF, and we know that the independence of these two random variables means that the joint PDF is a multiplication of the individual PDFs. This means the joint PDF, which is this one, is equal to the PDF of x into PDF of y. So now let us see how we can compute the expectation of product of x and y. So x is a random variable. It's a function from omega to real line. Y is also a function from omega to real line. So x into y, the product, it is also a function from omega to real line. So xy is also a random variable. Its expectation is defined in the following way. Because it is a function of x and y, we can use the distribution of joint distribution xy, which is f capital X capital Y bracket small x comma small y. This is the PDF, joint PDF, and then I integrate this multiplied by xy. So instead of just x or just y, I am using xy because this is what I want to compute the expectation of. So the expectation of xy is just xy weighted by the probability distribution that a capital X takes value x and small y takes value y, and then I'm integrating. Now we will use the result that they are independent. So I will replace the joint PDF by individual PDFs. So now we get a integration which is double integration on dx dy xy the PDF of x into PDF of y. Now because, and these limits are also minus infinity to plus infinity, and because they are independent, we can separate these two, this double integration to product of two one-dimensional integration. One integration would be made from x, PDF x and dx, which is this. Second would be made from y, fi y and dy, which is this. This is because all terms are separable. So now you can look at the first term. This is the integration of x weighted by the PDF of x. This is nothing but the expectation of x, and this is equal to expectation of y. So I can write this is equal to expectation of x into expectation of y. So what we get here is that the expectation of xy is equal to expectation of x into expectation of y. This is the result which we get when we are assuming that the random variables are independent to each other. Same way you can prove that instead of taking this particular function x into y, I can take any function of x and y and can prove this. So let's assume we take a function gx into hy. So I'm taking a map from x and map from y, and I want to compute the expectation of this. You can put these things in the same derivation, and you will see that because they are also product, we can separate them into two one-dimensional integration, and what you get is that the expectation of gx into hy is expectation of gx into expectation of hy. And just as you know that this expectation is with respect to xy, x and y both. So when I compute this, I integrate this gx hy into joint PDF of xy, x comma y, and these are expectation with respect to x and expectation with respect to y. Means here I am only using the PDF of x, and here I am using the PDF of y. Now let us take a little bit more complicated example. In this case, I assume these functions are, I am taking the function of xy which is separable, which means xy is x into y. Here also gx and hy are separate functions. Let us take a joint function where x and y terms cannot be separated. So consider a function g which takes values from range of x cross range of y to the real line. It means this function takes two inputs, one from the range of x, one from the range of y, and give us one value r. Okay, so this function can have gx comma y because x value can be from the range of x and y can be range of y. So gx comma y would be a number. Note that this is not xy, this is x comma y, which means g has two inputs, x and y. This function can be anything like x square plus y square or xy square, x log y, any kind of functions you can take. So now, what is the expectation of this function? So let us try in the first definition using the first principle definition. Expectation of gxy is equal to integration, double integration of gxy into the joint PDF of xy, and I will integrate it over the complete real line. Note that here I am using capital X, which means this is expectation of x comma y. Here capital X and y represent that they are random variables. So when I say gxy, it means this is a function of two random variables, x and y random variables. So I take these random variables and compute the function, and every time the experiment happens, xy will take some value. So gxy will also take one value. And I do this experiment multiple times. I collect all values of gx comma y and compute the average. Okay, so this is more like coming from the experimental point of view. Here I am representing them in terms of a deterministic integral. I am saying that the sample average, left hand side, which is the sample average, should be equal to the deterministic integral if I integrate the value of gx comma y weighted by the distribution of x and y. So here this xy is a random variable, but this function is a deterministic function of two variable x and y, and it is an integration of gxy weighted by that PDF. So this is the same as what we have discussed earlier. Now, if they are independent, this PDF can be written into multiplication of the two PDFs. So f x comma y of small x comma small y is equal to the PDF of x into PDF of y. Now you can see, because gxy cannot be separated into two products. It's a joint function. We cannot separate this into two one-dimensional integration. Although we can still divide this density into two parts. So let us reshuffle a little bit. We know that fyy, this is a double integration can be written in terms of two consecutive integrals. One integral with respect to x and another with respect to y. So if you look at this term, fyy is not a function of x, so it will not change the integration with respect to x. So let's take this little outside the dx integral. So what you get is one-dimensional integration would be gxy fxx dx, and whatever the value of this, I will integrate this with respect to PDF of y into dy. This is just some reshuffling of the terms. This will not change the value. Now let us look at this integration, the red one, carefully. If you look gxy and I am integrating with respect to x, for example, gxy is nothing but a function of x. So let us assume for now that I fix y, then gxy is hx. Okay, so y is constant, let's assume that. So in that case, gxy would be just like a function hx. So if I replace hx here, this will be an integration of hx fxx dx. So what does this form reminds you of? We are integrating hx weighted by the PDF of x. This should be the expectation of hx with respect to x. So this can be written as expectation of x with respect to x. And what is hx? Hx is nothing but gx comma y. So this hx, I just rewrite it back. This is nothing but the expectation with respect to x of g capital X comma y. Here y is constant, so that's why I'm taking as a deterministic value, just small y. While the rest case is showing that you take this, compute the function of the random variable, and I want that expectation. So let us put this back in this integration. So once I put it back, I get the integration of expectation of gx comma y fiy dy. Now we will apply the same trick here. This is an expectation with respect to x. So once you have computed this expectation, there is no x left. But this will be a function of y, because if you look at this term, if we change y, this integration will change, the gxy will change. So this will be the function, a function of y. So let us assume for now we denote it using hy. So this hy is different than that previous hx. They're just temporary notation. So you can think of this as a function of y hy. If you change y, this will change. So if I just replace hy here, then this is nothing but the expect integration of hy with respect to the PDF of y. So this can be written as expectation of hy. And what is hy again? H is this. So I can write that this is equal to expectation of y of expectation of x of gxy. So this is what you get here. That this expectation of gx comma y is equal to expectation of y with respect to y of expectation of gx comma y with respect to x. So first we will compute the expectation of this function with respect to x, and then whatever we get is a function of y, we will compute its expectation with respect to y. Or we can compute the joint expectation also, both are same way. So what this relation shows us that if you are given a joint function of two random variables, you can either compute the expectation with respect to the joint PDF, or you can compute the expectation first with respect to one random variable, and then whatever the result you get, you can compute the expectation with respect to the second random variable. And here I am assuming that these two random variables are independent. That is why this separation of PDF was possible. Now let us move to more general case. Let us remove the assumption that these two random variables are independent. So if they can be dependent, then we know that the PDF is no longer the function of the two individual PDFs, but it can be written as a product of the PDF of one random variable and the PDF of another random variable condition on the PDF of, the condition on the second random variable. So this just follows from the definition of conditional PDF. Recall, the conditional PDF of x given y is equal to the joint PDF divided by the PDF of y. So from that we get that the joint PDF is equal to the conditional PDF of x given y multiplied by the PDF of y. So this is at least in the product term. So we replace this in the original integration. So recall that we are interested in calculating the expectation of a joint function g of x comma y, which can be written as a two-dimensional integration of gxy weighted by the PDF of x and y, the joint PDF of x and y. So now we will replace this joint PDF by the equivalent product form, which is the conditional PDF of x given y multiplied by the PDF of y. Again, we will represent them in terms of two subsequent one-dimensional integrations. So first, I will consider about the integration with respect to x. So this can be written as integration of gxy fx given y dx. This is the first integration, and then the rest terms would be, this will be a function of y, so that will be integrated weighted by the PDF of y. Now if you look at this middle one, this is the expectation of gxy weighted by the conditional PDF. Sorry, integration of gxy weighted by the conditional PDF. So this is also expectation. Recall, expectation is something when you take a function of a random variable, multiply by the PDF, weigh by the PDF, and compute the integration. Here, this f x given y is also a valid PDF. So I'm taking a function of random variable x, and I'm assuming y is given. So given y, I'm computing this integration. So this is nothing but that's conditional expectation of gxy. So this is what I'm defining, that if you take any random variable, function of random variables, and multiply by the PDF, conditional PDF, and integrate it, what you get is a conditional expectation of gxy. So conditional expectation of gx comma y with respect to x given y is defined as the integration of gxy multiplied by the PDF of xy given y into dx. Similarly, you can also define, if they are discrete random variable, just replace the PDF with the conditional PDF. And then this is the inner integration. The outer integration would be, this is a function of y, given y, this will change. So once I integrate that with respect to PDF of y, what I will get is a expectation with respect to y. So I can say that the joint expectation of gx comma y, remember that I did not put xy here, but it is understood that it is the expectation with respect to all random variables which are inside. So unless something is stated, we always assume that the expectation with respect to all random variables. So this is expectation of with respect to x comma y of g x comma y is equal to compute this, first I will compute the expectation of this function with respect to x given y. So this is expectation with respect to x, but I'm assuming y as a constant. So y is given. So that's why I'm getting a conditional expectation. And then because y was earlier assumed to be constant, now I will decondition with respect to y. I will remove that y is constant and compute the expectation with respect to y. So once more, what I did is I first assume y is constant, and then given y, I compute the distribution of x and computed the expectation with respect to that conditional distribution. This is given y. Now y can take any values. So depending on the distribution of y, I again took the expectation of this conditional expectation with respect to y. And that is how I got the complete expectation of gxy with respect to both random variables. Again, I said here, once nothing random, no random variable is given, I will assume it's the expectation with respect to all random variables which are involved. But here you can see, here I'm saying x given y. So I'm explicitly saying that y is constant. Do not compute expectation with respect to y. Just compute the expectation with respect to x, assuming that y is constant. Assuming that y is constant. So that is why it's called a conditional expectation, because one of the random variable is conditioned to have a fixed value. So this is the result. This is the notation we have used, which I have explained also, that the conditional expectation of gxy given that y takes a particular value. So here I am saying that you want to compute the expectation with respect to x, assuming that y is given. Y is given means y is constant. So this means compute the expectation of gxy with respect to x given y. So this is denoted as integration of gxy weighted by the conditional PDF of x given y. Again, remember, if I change this small value y, or basically this means that if I change the y value of capital Y, random variable on which you are conditioning, this integration will change. Because if you change y, gxy will change. The condition distribution may also change. So this integration depends on the value of y. Even if gxy suppose does not depend on y, still it will depend on y because the conditional PDF may depend on y. So because this, if you look at this one, here I am computing the expectation with respect to x, but y is still a random variable. So if value of y would change, then the value of this conditional expectation will also change. So the whole expression is also a random variable because it is a function of y. Think of in a different way also. Suppose x and y are two random variables. You perform the experiment multiple times. Every time you get some values of x and y. That is what random variables means, that you will see different values of x and y. You compute a product of these two functions. That is also a random variable. You will see different values every time you do that experiment. If you take, instead of y, you take y square, you will also see different values of y square. That will be another random variable. Similarly, if I do this experiment and I compute that for every given, so there is some value of y, and I compute this function for that one. So I'm not recording x, what is the exact value of x. I'm only recording the value of y, suppose, and then I try to guess what is the value of x by doing this expectation experiment. So I have the value of y, I did the experiment, I have the value of y, I computed this particular deterministic integration because once I know the value of y, this is a function and y is constant. I integrated with the deterministic distribution. I get one value. I said this is the value of this term. Then I redo the experiment. I got another y. I again calculated this. That will be the other current value of that experiment. So every time I do this experiment, I get a different value. Those are actually samples of this random variable. Right. So you're seeing that every time you do this experiment, you get a different value of y, so you get a different value of this. So at every sample, you get a different value of this term. So this is like a random variable because every time it is changing value across different experiments. Okay, and its values will depend on the values of y, because if you're changing value of y, this value is changing. So this takes that particular value as the distribution of y. So let us take some more examples of this, which is actually special cases. Let us assume that gxy is actually just x. So it is, in general case, it is a function of both random variables. But let's just take a special case where gxy is just a function of x. but the formula will still be applied because it is for the general case. So remember that expectation of x given y of gxy is nothing but the expectation of conditional, the term with respect to the conditional period. So here expectation of x given y of x is equal to expectation of, so integration of x with conditional distribution of dx. Okay, so I'm computing the expectation with respect to x, condition on x, and I'm computing the expectation of the random variable itself, which is x. So this is just the integration of x weighted by the conditional distribution of random variable x given y. So remember that this conditional distribution is actually the expectation of, sorry, the distribution of x itself. Only difference with respect to a regular PDF is that here the value of y is fixed and you're only considering those experiments where the y takes those values. So this is the mean of x given the value of y. So if I look at only those experiments where y take this particular value, then out of those experiments, this is the mean of x. Okay, once again, so basically, when I say y is condition, it means I am not looking at now every other experiment. I am only looking at those experiments where y takes that particular value. Recall the conditioning distribution. What does it mean? When I condition on b, I only look at the experiments where b has occurred. So if I talk about probability of a given y, I look at probability of a intersection b, because all the a where b has not occurred, that is not no longer of my concern. I look at a intersection b because there b has occurred along with a. So here also, when I say that y is given, I look at only those experiments where y takes that value y. Okay, so if this is here y is given as 0.5, I'm only looking at those experiments where capital Y takes value 0.5. And out of those experiments, I collect the x and I compute its sample average, right? That will be the expectation of x given y, because then I have fixed the y and then I say, if you fix y, what will be the expected value of x? If you do this experiment multiple times, what is the uh, mean value? What is the value you can expect on the average coming out of x? Okay, this will give you another hint to us that suppose I do the experiment where x and y are both two random variables, and somehow I don't have a way to calculate the actual value of x. I can only observe the value of y. So from that, I have to guess that what can be the value of x. So there, this kind of conditional distribution can be also helpful, that I know the value of I know the joint distribution, so I can tell you what is the average of x which can happen in this case, although I do not know the exact value of x. We will come back to this later on when we also talk about the estimation of random variables. There we will see some more examples of how this conditional expectation is actually linked to estimation. Let's take another example. Here I am assuming gxy is a function of y only. So it can be just y square, or any function of y. It does not depend on x. So if you put this in the formula of conditional expectation of x given y, if I put you in the integration, you will see that this is equal to hy into PDF of x given y into dx. Now this is an integration with respect to x and it does not depend on y. So I can take hy outside because it does not depend on x. So if hy is outside, this will be an integration from minus infinity to infinity of the PDF dx, conditional PDF dx. No matter whether this is a conditional PDF or the regular PDF, the integration will be 1. Okay, we have proved that this is a valid PDF. It means the integration is 1. So if this is 1, this I will only get hy. So conditional expectation of any function of hy with respect to x given y is nothing but just hy. And this is intuitive because y is given to you. If I know the value of y, hy is just a deterministic value. So even if I compute this expectation, I do not require many samples. I know the value of y, so hy is deterministic. So conditional expectation should also be hy. Remember that I am computing the expectation with respect to x, not y. If you compute the expectation with respect to y, things will change. We have already computed what happens when we compute the h of x, so that you can consider. So we can again see that this was the first part, but if you have this hy function and then you want to compute the expectation with respect to both random variables x, y. So suppose I want to compute the expectation with respect to joint distribution of x and y. Then I can use the result that first I will compute the expectation with respect to x given y, and then I compute the expectation with respect to y. So if I write this will be expectation of x given y of hy, and then the resultant I will take the expectation with respect to y. So this term I have already proven that this is just hy. So this will be expectation of phi of hy. You can also prove this by using the first principle formula that expectation of hy with respect to both random variables is hy weighted by the joint PDF of xy, and then into the conditional PDF multiplied by the PDF of y. Then because this function does not depend on x, and this also does not depend on x, this also does not depend on x, I can take them out. So this will be integration of hy fi dy, and this will be the integration with respect to x will come inside, and which only have the term fxy dx. This is a valid PDF, so it becomes 1. So what I get hy fi dy, which is nothing but the expectation of hy. So what I saw that if I take this should be capital Y. So if I take a function random variable y and compute the function of that random variable and compute the expectation with respect to all random variables x, y, I have to only compute the expectation with respect to y only. These will be equal. So many times if you do not see the this term, you just see expectation of hy, and then you are wondering whether you have to compute the expectation with respect to xy or just y, it does not matter because both will give you the same answer. You can generalize this result saying that if there are many random variables like x1, x2, xn, and suppose there is a function of only two random variables x1 and x4, then the expectation with respect to all random variables of this function is equal to expectation with respect to x1, x4 of these two. This you can prove by writing the joint distribution of all those random variables. So sometimes you will see a shortcut that people only say expectation of h of x1 comma x4. They do not explicitly mention you have to compute expectation with respect to what variables. So that is not actually required because always remember you if nothing is given you have to compute the expectation with respect to all those random variables which the inside is a function of. If you include any more, that is okay, it will not change the answer. But you cannot skip any of those random variables. We will now learn an important result where we will see that expectation is a linear operator. What does it mean? That if you take expectation of summation of two random variables, then that can be written as the summation of the expectation of these two random variables. So let us see this example. Suppose the function of two random variable g is equal to is like this, that g of x1 comma x2 is x1 plus x2. Then the expectation of g x1 comma x2, and this is an expectation with respect to the both random variable, is given in the following format, and that can be calculated by taking a double integration of this function, multiplying it with the joint distribution. This is the standard definition of expectation. Now, because the integration is a linear operator, we can break this integration into two parts. One will be the integration with respect to x1, second would be on x2. Now, if you look at this, I am computing the x1 multiplying by joint distribution. So this will be nothing but the expectation of x1, and this one would be nothing but the expectation of x2. You can also explicitly, if you want to see this, you can also proceed in the following way. You can first take this inner integration on dx2, and since x1 is not dependent on x2, it will be outside. So now this inner integration is the integration of joint distribution over x2. So this will be the marginal distribution of x1, which will be given by this. And now it is x1 joint distribution of x1. So this will be nothing but the expectation of x1. Similarly, you can take here x2 outside and compute the integration over joint distribution on x1. And here you will get the marginal distribution of x2. This will be expectation of x2. So what we have seen is here that expectation of summation of two random variables is equal to the summation of the individual expectation. You can extend this result to any summation of any functions of two random variables. So if there is a gx1 plus gx2, or even g1 x1 x2 plus g2 x1 x2, then the expectation of this would be equal to expectation of g1 x1 comma x2 plus expectation of g2 x1 comma x2. So in these lectures, we have seen some important properties of expectation, which we are going to use in the future also. I will revise them. So expectation, as is defined as, for discrete random variable, you sum over all the values in the range of random variables. You take the value of gx and multiply it by the probability of that random variable x taking that value, and then sum it. For the continuous random variable, this summation becomes an integration. You integrate the value gx with the probability that x takes value in the interval x, which is fx dx, and then you compute the integration over the range. First property which we saw, that if x and y are independent random variables, in that case the expectation of gx and hy is equal to expectation of gx into expectation of hy. So expectation can be broken into the product of two random variables if they are independent. Second property, we have seen that if there is a function of two random variables x1 comma x4, and these random variables are defined on the same probability space, and if I am asked to compute the expectation of this function with respect to all random variables, then I can just omit the random variable which do not affect this function and can only compute expectation with respect to these two random variables which actually affect h, and that will not change the distribution. It will not change the value. And the third property, we have seen that if there is a function g x comma y, and I have to compute the expectation with respect to x comma y, then I can first condition on one random variable, let's say y. So I can condition on one random variable and compute the expectation of this function with respect to x given y. Whatever would be remaining, would be a function of y, and then I can, that's also a random variable, I can take its expectation with respect to y. So this is known as the conditional expectation law, or sometimes chain law also. This conditional expectation, let me remind you, is computed by the same formula, but instead of having this distribution, we will use the conditional distribution. So in case of discrete random variable, this will be PM of condition and y. In case of continuous random variable, this will be PDF with of x given y. So if we have two random variable x and y, they can also be characterized using their covariance and correlation. Formally, covariance of x and y is defined as expectation of x minus ex into y minus ey. And if you multiply it, you will find out that this is also equal to exy minus ex into ey. Correlation of x and y is defined as covariance of x and y divided by the square root of the product of variance of x and variance of y. So covariance of xy is a normalized version of covariance, and it can be shown that correlation lies between -1 and 1. When correlation is 0, then we call the two random variables uncorrelated. If this is 1 or close to -1, then these random variables are called to be are known as highly correlated. If x and y are independent of each other, then we can show that exy is equal to ex into ey. If you integrate xy fxy dx dy, then this integration breaks into two parts. This one is ex and this one is ey. So in that case, if you calculate the covariance of xy, it comes out to be 0. So correlation is also 0. So for independent random variables, covariance and correlation are both 0. If there is a random variable z such that is equal to x plus y, then the expectation of z is equal to expectation of x plus expectation of y. We have already seen that. We can also calculate its variance. Recall that variance is defined as expectation of z minus ez square. Z is x plus y and ez is ex minus ey. So I can take this term, I can take ex with x and ey with y to get expectation of x minus ex plus y minus ey whole square. And then I can expand this term as expectation of x minus ex square plus expectation of y minus ey square plus 2 expectation of x minus ex into y minus ey. This is variance of x and this is variance of y, and this term we have called covariance. So the variance of z is variance of x plus variance of y plus 2 into covariance of x and y. Again, notice that if x and y are independent, then covariance would be 0. In that case, variance of z is equal to variance of x plus variance of y. So if you add two independent random variables, the total uncertainty or total variance is just summation of the two. But if they are dependent, the variance may increase.